y'all, and a happy new year, and welcome to another high-powered episode of the High Voltage Live Show. I'm your host, Willie Snyder, with NEC Code, coming to you live from the Mile High City in Denver, Colorado. I'm joined by my awesome co-host, Mr. King James Stallcup of Stallcup Electrical Education, and he has an awesome segment that's totally geared up for all you guys who are trying to pass the Journeyman exam. We thought about it for a while, and he decided to release a free Journeyman exam prep course. As long as we'd really like you guys to subscribe to the channel. We're going to try to hit a goal of 1,000 subscribers in 12 weeks. And so get your uncle, your aunt, your grandma, whoever to subscribe to the channel. And then we got you a free Journeyman exam prep course coming every week on our topic of the week. And I'm really excited, James. We've been building up for this for a while. And nobody else out there is doing stuff like this. And so we wanted to be the first to come out there and do something like this for all you guys trying to pass the Journeyman exam.
Sure. Well, actually, it's for Master or Journeyman. These are, I'm going through the calculations. I mean, it's going to be, by the time we get there, it may even take more than 12 weeks, but it's going to be intense. We'll start off easy with some Ohm's law, pi formulas, AC, DC formulas, and then we'll jump in from there and get into our AC circuits and DC circuits, and we'll go in and talk about all of those. And then after that, we'll get into the understanding and layout of the National Electrical Code. And then after that, we get into wiring methods. Then we get into sizing conductors. Then we get into sizing overcurrent protection devices. Just those two are going to take a long time. And then we'll get into doing residential calculations and then finish it off with commercial calculations. Now, as far as just answering questions out of the code, I'm not going to do any of that. All the stuff that I receive from everybody, like, man, I wish you'd do more calculations. I understand them better when you're explaining them to us. You make it so easy. Yeah. And I said, well, you know, Bill and I talked about it, and I said, let's just do one, spend about 3-4 months on prepping for Master or Journeyman, and we also tell people about it, let them know we're doing it, and we do wish you subscribe to the YouTube channel. It'll be over on Stallcup Electrical Education. It's in the description that you log on there, and make sure you smash that like button. So other than that, that's what I'm going to be hanging out doing. And I want to say one thing, a lot of what you're going to see, there's a lot of time that's being put into this. It just isn't just something, you know, somebody's throwing together. I'm actually going to do an example calculation, and then we'll get into the exercise problem where you fill in the blanks. Now, what I'm not going to do in this, and I didn't fill any of the blanks in. And the reason I didn't do that is somebody may want to go back and just stop right there in the video, and you can look at it and have a piece of paper, have your code book, and try to work it, and then you can play through and listen, and I'll explain all the values, everything, how they went in. And probably when we start getting into the code section of it, I'd probably say everybody probably needs to have pen and paper, and probably make sure you have your code book and have it on the 2020, because we're going to do it on the 2020. The 2023 has been updated, but I didn't have time to go back and get all the illustrations set up for this. So we're going to do 2020, and maybe starting next year, we'll do the 2023 portion. And,
look who popped in the house, Mr. G.
Yeah, you know I got a Texan accent, brother.
Yeah. You're going to learn about the motors, all right?
Motors. So. Yeah. Percy Johnson was fighting them the other night.
So, like there's a lot of people out there that charge like a lot of money for the, Journeyman exam prep. And all we're asking is just to subscribe to the channel. That's it. So it's pretty cool. We're really excited about doing this. It's really awesome. I already have a bunch of people popping in the house. I already see. We've got Mr. G in the house and stuff. So it's going to be awesome to be doing this. And like I say, it's just really awesome content that we've been putting together. Like I say, the myth of the week, I already have a myth for next week, the week after stuff. And
I do got one thing. For us, if you want us to know who you are, it's probably to be better that you go to the YouTube site, because I think it is the YouTube that shows us who is commenting in the comment section, and Facebook just shows Facebook user.
And Juan, Mr. G, you set it to private last week, so he could only get on from the Facebook side last week.
I fixed all of that.
It's all good. Yeah, you guys are all back up on YouTube now, so it's all good. But I think you're going to really love the meme this week, James. I had this happen to me, and I saw the meme, and I was like, I got to run this one.
All right, let's run it, see what it is.
I said, where's my tool? Yeah.
I've done that many times. I've done that, even like your phone or just something, you just had, where the hell did I put that thing? But the best part of that is going to Biden. We're getting all political up in here. I
try not to.
I don't usually comment on too many political posts, but I actually did one today, and I forgot who submitted it, but they were showing Trump next to Jeffrey Epstein, and there were a bunch of women around and stuff, and then somebody come down and they had the thing that was a published list of all the people that went down to Epstein Island, and I was looking at it, and I said, well, my comment was, I said, well, they definitely knew each other. I said, but a picture can be deceiving. I said, based on the list that I saw that somebody posted, I said, I didn't see his name on there, but I did see Joe Biden's. And I was like, that's part of it, just like teaching code too. Some boom, boom, boom are saying this, and this. And they give you a false impression of something that really isn't true, and say something, it's like, where Paul Abernathy said, he's riding daddy's coattails, he ain't done nothing, and here I got all of these industry achievement awards on all these committees and everything. Doesn't, just makes a false statement. That's sort of what that picture was. And I was like, if you're going to post something like that, at least tell both sides of the story,
True.
And
that's what I thought was funny. Just to let everyone know, I'm turning these all into podcasts through the Nat King Code podcast, and I did one for on 210.8F through ECNM, and it's really funny because he says, "Oh yeah, this is required whether cord and plug connected or hardwired." It's like, well, wait a minute, cord and plug connected is already covered in 210.8A. So why would you need that? Like, if you're gonna cord and plug connect it outdoors, then it's gonna be already covered because you'll be connecting to a receptacle.
Well, we're gonna find out here soon. Oh, one thing I will point out to everybody on the YouTube channel, there's gonna be a lot of stuff that's about to be taken off that's on there right now, because everything's being refreshed, redone. We're gonna actually categorize the High Voltage Live podcast into playlists for 2023 and 2024. So that way they'll be easier, and you can go find what was done within that month. So that's going to be something else we're going to do.
Mr. G's over on YouTube now. Right on, sir. Thanks for joining tonight. Appreciate you coming in.
That's right. Get over there, subscribe, hit that like button, baby.
we always love having Mr. G in the house. He always has a lot of good questions. So
One's cool.
Pretty awesome having you join. Yeah, so
right, let's do your myth. I got a lot to do tonight. You're going to keep me busy.
Good.
Matter of fact, I'm going to try to get as far as I can, but we'll probably take and either a new subscriber. Oh, we got another one besides him, Brent Hillman. Thank you for subscribing, brother.
All right.
But
Yeah.
we'll get as much as we can. If I have to carry it over into the next episode, we'll do that. But we'll see how.
I am really anxious to see your take on this. We've argued this a lot over the years, so I
Don't
think
worry.
you guys will all like this.
I love this. It was funny because when you asked me about it, I went back and I checked. I'll try.
All right.
So we'll cover.
That's cool.
All right, let's cue it up.
It's time for Myth of the Week.
All right, and before we start, looks like Mr. David Engelhart is up in the house, and he's over there on LinkedIn. So awesome! Thanks for joining us on the LinkedIn.
I subscribed to him a little later, and I wanted to, but I sent him a message back today. I've been so busy with other things, I hadn't even been on the site. I was trying to get everything ready, and I sent him a comment back today. So.
All right.
Well,
thanks for joining, Mr. Electrical Wizardry. Yeah, so awesome. This is Myth of the Week number 92. If you guys ever want to find out where these myths come from, I actually post the myths and the code sections and everything after I do these on NEC for Dummies, Electrical Code Discussion for Awesome Electricians, and now our new group, the Electrical Codes and Standards Discussion Group. So I'm going to be trying to contribute as much as I can to those. This is really one of the ones we've argued a lot in there, where I've had inspectors tell me, you can't put those zip ties in there because you're bundling. Well, bundling is not illegal, and bundling is not a code violation. And what a lot of times this gets kind of misconstrued a lot, that they just say anytime you're grouping these conductors together that you're creating kind of like a hot spot in the in all these conductors when you're grouping them together like this. And from what my understanding is, it says where spacing is not allowed or separation is not allowed, and it's not provided, you know. And so the way I look at this, you have a zip tie, it's grouping all the conductors together, then you allow spacing, then you're grouping them together, then you allow spacing. That's the way I look at it. But the whole thing is, I've never seen using zip ties as any kind of a code violation. Is you're just trying to dress the panel up. You're trying, you know, a lot of times they're grouping them where, you know, you have multi-conductor cables coming in and you're trying to group them to identify that neutral and stuff like that. And, you know, yeah, so it looks like David got your message over there.
Awesome.
So, yeah, awesome, sir. But one thing that this kind of comes into is a lot of people misconstrue this with like the 3 or more current carrying conductors grouped together, and a lot of guys will sit there and say, oh, well, you can only do 9 in there and stuff like that. So it's really funny when I came across this, I just really enjoyed this, sharing this myth with you guys, and then actually getting James's take on it, because I literally have no idea how James is going to handle this one. And so that's why I was talking to you on the phone the other night, James. I'm like, dude, I was like, I think I might have a hard one for you, but it might be an easy one. So the whole thing was that this is something that's been argued. I've actually had people on the job site like, oh no, they actually told us to use zip ties inside there, you know. So it's funny how you get so much contrast, where some people will say it's all right and some people will say it's a code violation. So I really like seeing both sides of this coin. And to me, in my opinion, I think this is 100% myth. I don't see that's considered bundling, and I feel it's 100% permitted in the 2020 NEC.
It is. It's false. All right, let me get in. Now, like you said, you get in and you start looking at adjustment factors. And like you said, that's where they get in and they talk about where you have more than 3 current carrying conductors. But one thing I will point out is, and you'll remember I did this. This has been about a year ago, maybe a little bit longer. But people were asking me about doing adjustment factors and correction factors, or a combination of both. And what I did is I went in and I actually took the branch circuit and I showed how to size for 210.19 A1A and B. So if I didn't have where I had the 3 or more current carrying, or if I had more than 3 current carrying conductors, I showed the calculation with 3 or more, then I showed it without 3 or less. So as I started looking at that, I went in and I showed how to apply all of this. And then at the end of it, I went over and I took everybody to Annex B, and where I started showing how to do adjustment factors for more than 3 current conductors with load diversity. And if you remember, as we went through that, I was even showing where you could have other conductors in there that didn't even have any load on them at all. And it even recognized where you had neutrals and things like that. But what this got into is where I could have the conductors in there, and all those conductors could be on pulling so much amperage, but yet the other half may not at the same time. So
and Juan brings up a good point here, about grouping makes sense and everything, but, so this is another thing I was going to kind of get into too, Juan, is that anytime you have this grouping, it doesn't matter what, the breathing or the, heat dissipation is. If that's less than 10% of the run, then that is actually going to act as like a heat sink. And I know that James will probably cover this, but if it's less than 10% of the run, then it's not going to be a factor in that circuit.
Well, I'm going to give you a couple of things to think about here, okay? That's just the first one through the information note. Now, if I look at 310.15C1, it says, and you remember me talking about this the other night, I said, it says, the ampacity of each conductor shall be reduced as shown in table 310.15C1. Everybody knows that. Where the number of current carrying conductors, now listen to this, in a raceway or cable, okay? Now, then it says, or where single conductors or multi-conductor cables are not installed in raceways, are installed without maintaining the spacing. Now, let's just think about that for a second. Okay, let's just say that.
Welcome in, Mr. Jake Riddle just joined up. Awesome. Thanks for jumping in, Jake.
And he's right about that on allowances, and that's where you're getting into a raceway and things like that. Now, let's think about this. Now, if I'm sizing the amperage that's inside that panel, I can tell you, because it was going into a raceway, you're going to size that based on table 310.16. But now you got to remember, now you're going to have to change the dynamic if you're going to say this is bundling, because now you're in an open enclosure. That's called free airspace in there. Now you're using table 310.17.
Okay.
There's a difference. And that's why when you go over and look at motors and you go look at 430.72B, and you pick that up over there, they've got table 310.16, and then they have 17. 17 is where you're in the enclosure. That's open air space. So the dissipation's different than what it is in a raceway.
True.
Okay. Now I hadn't had the chance to go over and look at any of the comments, on this, but I'm just curious. Did anybody bring that portion up?
There was a lot of 24-inch references in there.
This has nothing to do with 24 inches as far as the free airspace is concerned.
Yeah, and I agree. There's a lot of people that said they got called on this by the AHJ and stuff, and that the AHJ made them cut the zip ties out and stuff. So that's why I really wanted you to cover this, because it was really awesome, and I've actually encountered a lot of this kind of myth stuff before myself with the AHJs, just seeing a lot of this language, and they have that 24-inch in their head I've actually seen them try to say the actual board studs were actually considered a nipple, and stuff like that. So that's why I'm just real excited about you, covering this, James, and so far I'm not disappointed.
Yeah, and that's where my argument would be with them. I'd say, what amperage am I applying here? Because you're going to have more amperage when you're in free airspace. So if somebody wants to come in and say, oh, well, you bundle them 24 inches, say, well, if that's the case, I'm in free airspace, I got plenty of amperage. That would be my argument if an inspector was going to argue that with me. Now, I don't know if anybody has argued that point to that, but that's where I would be at that point.
Now, yeah, and David freaking nailed this one too. I really like that, David. That was a really good point that you brought up about 310 14A2.
I actually have that one, and I'm going to explain that too. Okay. Now, as you go in and you look at the informational note number 2, you'll notice that they're still making adjustment factors and everything in here. And this is where you get in to dealing with your bare or aluminum bars where you're in auxiliary gutters. Okay. And it's going to refer you down to look at 376.22B for your adjustment factors. And when you get in, you start looking at this portion here, it tells you the same thing, that it doesn't apply to the conductors here in raceways having a length not exceeding 24 inches. Now, I do want to point something out, and I've made this statement before. I've stated that anything that's 24 inches or less is a nipple, okay?
Right.
It's not a raceway system, and therefore the rules in Chapter 3 don't apply. This is the same concept here, and that's why you got bundling and all that. Everything's 24 inches. There's a reason all these distances are matching. And that's why we're not applying any adjustment factors here. Just like if I had a nipple that was 24 inches or less, I'm not going to apply any adjustment factors for that. Okay? Now,
what if I had a 24-inch panel? No, I'm just kidding.
You're reaching now, brother. Okay. Now, look at this. Now, D, this talks about adjustment factors shall not apply. Look at this, AC cable or type NC cable. And this is something that I brought up yesterday, and Bill called me about this, and I was saying, well, when you get in, you start looking at it, it'll tell you even for AC or MC cable, it doesn't apply to what? And then I think I said 3, but it was actually 4. It says, not more than 20 current carrying conductors are installed without maintaining spaces, are stacked, or are supported on bridle rings. Okay, and then you go down and look at exception 4, and then it does it once again. It says more than 20 current carrying conductors are installed longer than what? 24 inches.
Yeah.
So
and I think a lot of people are kind of off base on this too, Mr. G. Like the neatness and everything, and I just don't see the overheating of the conductors inside that panel, because you're basically in like kind of a free air environment, and I don't see that demand power to be increasing exponentially. But I mean, that's just me. I just don't see it. Like I say, if you're dealing with, let's just say you're bundling number 12s, you're actually going to be sizing that off the 90-degree C column, so you're going to be a lot different than when you're sizing that off like the raceway. So I don't see that being any kind of like a real world issue, sir.
Right. That's why I wanted to bring it up, because if you look at table 310.17, the ampacities are higher. And the reason they're higher is because you are in free air. And and I think that's why you're not worrying about bundling in that panel, because and plus, it makes a neater looking installation on top of that. But I believe you've got so much air in there for dissipation, it doesn't become a problem. And every place that I look in here, it really is getting into where you're stacking on top of each other. They're all right next to each other. You're bundling together. They're not just out in free air. It's in a raceway. It's something like that. And
Yep.
I think that's what you have to look at. Now, if you were just taking cables and bump, yeah, I think you got a problem there because you got insulation around those conductors and it's hard to dissipate. But when you go inside a panel board, you've stripped those cables and everything, and now those are conductors in free air. You see what I'm saying? It doesn't have insulation and everything around it that's holding that cable together.
And when I do mine, I'll usually do like a zip tie at the top, and then they'll kind of go as a loose kind of bundle, and then I'll do a zip tie, down a little bit halfway. But I'll use maybe like 3 zip ties per side, and so I'm actually allowing for spacing. One is the way I look at it. That they're, I have them all bundled together. Then there's space where you could slip a conductor through there, and then they're bundled again, so it's not like they're just all bundled together as tight as you could possibly get them through that whole section,
Sure, there's enough air there for it to dissipate. So, and then you look at 14A2 exception. It talks about it where you have different ampacities, and it tells you it applies to portions of a circuit, and the higher ampacity shall be permitted to be used if the total portions of the circuit with lower ampacity does not exceed 10 foot or more, okay? Right. Or 10% of the total circuit. So you can come in and look at this, and that will take care of it also, in my opinion. This is just based on the way I read the code. And my main 2 sections really, is table 310.17, because if I go back here and I look at this right here and I look at my adjustment factors, I'm going to be applying that based on table 310.16 because these are contained within what? A raceway or a cable.
Yeah.
All right. Then if that's the case, then my main focus at that point is table 310.17 because that's where the table for free air conductors, and then 310.14A2 exception. And I guess by what was just said, I'm assuming David Englehart mentioned this in one of the comments.
Yes, okay. He did.
All right, well, David, I agree with you, brother. I'll tell you right now. But that is the way I view that. And the most important part of that to me is table 310.17. I think that is the overriding factor in my point because it is free air and you're not applying the same way that you would. Because if I go in and I actually look at that, you look at the requirements for more than 3 current carrying conductors, you're usually looking at doing that when you're inside a raceway or something. And
I just wanted to respond to Juan here. I really think that you're kind of a little bit reaching here, Juan, because I don't really see that being like an issue in this situation, with like panel boards, everything like that. I mean, you're not going to have like multiple ACs coming through that one panel board, You might have one AC unit that's running 24/7, and then that's bundled with something that's non-coincident load that's possibly a heater, that stuff like that. So I just don't really see that being a factor.
Well, I mean, we get it even worse here in Texas. And thank you very much. Love it, David.
Awesome, David.
Elvis has left the building, baby. But here in Texas, I've inspected many where they've gone in and bundled and everything. They got all the AC units on those big commercial buildings. We ain't never had a problem with the inside with conductors burning. The only time I ever see a problem inside a panel board, it's usually due to a loose connection.
True. And yeah, Juan, we really love your comments in here. It's really awesome having you. And it just comes down to there's really not a potential adverse effect that we're seeing in this situation, just based on the amount of free air that you're gonna have out there, that's gonna not cause any kind of a overheating issue. So that's kind of where our point of view.
I'll give another example. How many times have you seen a wireway? You can go up to 30 current carrying conductors in that wireway, and then once you get over that, you have to start applying percentages, based on the extra amount of current carrying conductors. But you get in there and you look at that. I've gone in and been inside wireways that were completely stuffed, but it didn't affect the circuitry or anything. It was just that enclosure was hot as hell,
True.
and that's what you're looking at. And the reason that is because there's more air to dissipate in there than what there would be in a raceway. And I know a lot of people are saying it, but I would fail that installation, because they didn't apply the proper adjustment factors for all them current carrying conductors. But I have seen that.
Yeah, and I agree with Jake here, because there's a lot of times where we deal with like stranded wire, and you have to kind of use zip ties to make it clean up, and like, that's pretty funny, Jake. But like, the whole thing is that what we run into, like, I try to not use zip ties on like solid wire. I try to square them off, do nice 90s and stuff. And I've actually had times where I made up a panel and I've looked at it with no zip ties at all, and I'm just like, wow, that's pretty good, But then I'll go back and I'll maybe have to add some circuits, and then I'm like, the easiest way to do that is just kind of loosely put a zip tie at the top, kind of, and then bring my new circuits in, square them off, then hit the zip tie. Then it'll just make my first neatness look just that good, So it's kind of a skill that we've learned through the years, and I don't think that there's any reason to worry about zip ties and bundling or anything inside an enclosure.
Well, I can tell you in Texas, we don't have a problem with it. At least when I was the chief in Grapevine, I mean, everybody, make the panel look good, and made zip tie and fix everything up real nice. Never had a problem with it.
Dude, I had one time we were doing a job, and the inspector came out. He must have been a new inspector. I'm just giving him credit, But he looked at one of my panels. He said it was the best looking panel he's ever seen since he's been inspector. Okay. And I thought to myself, I was like, that guy's seen a lot of panels. I was like, that's pretty cool. It meant a lot to me, to hear that. But yeah, and that's cool. We'll see if that happens there, Juan.
Took them horns, baby.
Yeah.
Even though they lost, that's all right.
Yeah, it was a good game. Like I say, it brought us entertainment for the college football. So, with no further ado, we are gonna do the topic.
All right, let's roll it.
So. So I just wanted to get it straight. So the topic is going to be our Journeyman exam prep course for the next 12 weeks, correct? Or longer.
Or longer. It'll be master and Journeyman exam prep.
Okay.
I'm going to go through a lot of really good calculations.
I'm going to be a master one day, but not today. I have to go with David Engelhart. Go Blue. I'll have to give a big Go Blue shout out to my brother. My brother's a big Michigan fan, so.
I think Michigan, they're probably going to win. They got a good team, so.
Yeah, I
But
agree.
Washington had a better team than I thought they did. I didn't think there's no way in hell they were beating Texas.
Yeah,
But I was wrong. I'll say one thing: their quarterback's good. God dang, he's good.
yeah,
So,
yeah.
all right, let's get it going.
So, it's all good.
All right. Now, the first thing that's going to happen, we're just going to look at applying some AC/DC formulas. And what I'm going to do here is I'm going to go through all the different formulas and everything with an example problem. And then what's going to happen is I'm going to go to the next one, which is going to be an exercise page. And what I'm going to do is I'm going to let it set up there for about 15 seconds. And anybody that wants to watch the video, you'll have like homework, I guess. And you can go grab a piece of paper and I'll show you here in a little bit. You'll have A, B, C, D, and you'll go in and work the problem. And then next week when I come back, I'll give the answers on that, and then I'll get the next setup for the next lesson. We'll go through all the example calculation, and the next week we'll have the exercise problem and go over it again. Okay? So,
Hey, I have a question though.
mm-hmm.
So is there a way we could set up like a stupid question for like the end? Like everybody could just have their own stupid question for like the end of it. Like my stupid question I always think about is, what's the difference between kilowatts and kilovolt amps?
Sure, we can do that. If you want to ask that, then I'll put it at.
Yeah, like when you're all done with your
Week.
lesson, whatever. Yeah, whatever. It would just be like everyone's entitled to have like their own stupid question, and they don't have to all be stupid, but just some question that they want to ask, And
Okay, yeah, we can do that.
That'd be cool.
Okay, now as you look at your AC/DC formulas, you got some certain letters that are used, and when you look at those, they mean something. So anytime you see I, we know that's amps. Anytime you see E is volts or V is volts. PF is power factor. KW is kilowatts. KVA is kilovolt amps. HP is horsepower, and EFF is efficiency. Those are the terms we need to know when we're looking at applying AC/DC formulas. Okay? So when you come in and you look at this is just a basic thing that we put together. It's in our publications. And basically we tell you what type of calculation is, where it's direct current or alternating current. And then you come over to the left-hand side and we'll tell you what is it you're looking for here. Okay? And then you come across, and based on whether it's direct current or you have a 120 volt circuit, you have a 208, 230, 240 volt, or anything that's three phases above. These are the calculations that you're going to use. Now, anybody that goes through any type of apprenticeship or anything, these are formulas you need to learn. And the reason we always start with this is because when you get into some of the examinations, they're going to make you calculate and find some of this information, knowing how to apply these type of formulas. Okay?
Sure.
And then you'll get your question. As long as you knew how to calculate using these formulas, you're not going to have a problem. So
yeah, I actually enjoyed when I took my last test for the NISAT 2, just off of the way you explain this. It was just, you're really confident when you do your calculations.
Sure.
Because you know that whatever answer you have, it's the right answer. You don't even have to second guess it.
Sure. And you can tell by just the things they're asking. Like here, we know the horsepower's known. Okay, so we got 40 horsepower here. It's 460 volts. It's a three-phase induction motor. And then look, they're telling you I've got a power factor of 90%, and then I have a operating efficiency of 85%. Okay, now what I always like to teach here on this is, first you want to take the horsepower and multiply it by 746 watts per each watt. That's what you're going to use is the the number 746. Now, after that, everything's going to divide into that. So then you got 460 volt. It's three-phase. So for three-phase, we use 1.732. And then you've got 85% efficiency, 90% power factor. You're going to multiply all that together. And that's going to give you 609.5 volts. And then you take the 40 horsepower times 746 watts, and that's going to give you 29,840 VA. And then you just take the voltage, divide it into the VA, and it's going to tell you the amps are 48.9 amps when the horsepower is known. And the horsepower will include what? That power factor and operating efficiency. It's pretty simple. And when, I was, I've been teaching for a long time, and I actually went out, I was doing a class out at Pantex out in Amarillo. That's where they do ammunition and stuff for the government. And they wanted me just to come out there and go over these calculations and explain them. And they even had their engineers in there to make sure they knew the proper amperage ratings when they were applying any type of new installations, because they were always adding stuff out there. Okay.
Right.
Now, the next thing you're going to look at.
Juan has one for a stupid question. Full load amps versus full load current. So.
Okay, I'll cover those two next week. All right.
Yeah.
I do them right now, but there's so much to do.
Yeah, just do your thing. I just want to make like a stupid question thing. Like anybody could ask their stupid question, we'll cover them.
No worries. All right. Now, when you get to this, I'm not going to cover this right now because I'm going to let everybody go back and work this. But you're going to notice we're going to give you known values that are in here. So you've got a 5 horsepower motor. It's 230 volts. You got 80% efficiency and 90% power factor. It's a 230 volt single phase. The only difference in this one than the other calculation is it wasn't three phase, so I didn't have to put the 1.732 on there. Okay?
Right.
Just giving everybody to get them used to this. And what you're going to do is you can go back, look at this, and all you're going to do is you'll see right there on the right-hand side where it says exercise problem, and you've got all the way to J. You just put A, B, C, D, put your answer in. Next week you come here, we'll see if you got it right. And if there's something you didn't understand, then you ask me a question on it. Okay?
I like it.
I gave this a lot of thought, and I thought I could just go ahead and give them everything. Then I thought, it might be good to let them be able to work the problems and then come back and look at them. And this way, it's sort of like a classroom instruction, if that makes sense.
Yeah.
So.
Yeah. No, I love the way you do it. It made me way more confident when I went to take my test, just because I knew that when I had the right answer, I mean, I was smashing it. I was like sitting there, oh, yep, right, correct.
Sure.
And that's the whole reason I made the NEC Code page, was to make sure you guys are confident in your, taking this test. Like, you're going to go in there, you're going to pass. There's not an option of fail.
Well, and I think people come in, they listen to this podcast, they're hearing easy ways to do things. And like, here's another, this is where the kilowatts known. So I got 54 kW load. Now let's look at what we have. It's 240 volt single phase. And look, they have a 75% power factor. Well, like I said, we're going to put it in VA form, or watts, whatever you want to call it. So you take the 54 kW times 1,000. And then everything else goes over there and multiplies again. So you take the 240 volt, I had 75% power factor, that gives me 180 volts. Divide that in to what we calculated first, just taking the load, and that'll give you 300 amps. Now, the reason I like looking at this, because this was not hard. If you notice, the first one we did, we got all the VA form, then everything else was to the right, wasn't it? And it all multiplied together. Okay? And a lot of people get confused a lot of times. Where do I put this value? Where do I put this value? Just come over, take your load, get it in VA form, watts, whatever, and then you're going to divide whatever's left, and you'll multiply all that together to divide into it, and that's going to give you your amps. Okay?
Yep.
So when you come over and you look at this, and same calculation, there's only one difference. We did it in 3-phase. So now if it's in 3-phase, we're adding the 1.732. And in step 2, we gave you the formula there. And then if you look in the middle, we got formula requirements, and you can see all the different formula requirements that could be there, that could apply to that calculation. So if I didn't have power factor there, then it'd just be the voltage, wouldn't it?
Yes,
see
sir.
that? That's what you're looking at here, is going through and getting used to these formula requirements. And I can tell you, I've seen a lot of publications out there and think none of them are set up like this. These type of illustrations took us, I'm just telling you, it takes a lot of time to develop these type of illustrations and all these fill in the blanks and stuff. Okay.
Well, yeah, I mean, you had to get that outlet in there on the left hand side.
Yeah. We're going to find out about that. Okay, now look at this, and this is where we know the kilovolt amps. Now, if you look, I don't have any power factor, I don't have any efficiency or anything. It's just 240 volts. So I'm going to take the load at 1,000, 72,000. Then everything that's left goes on the right side to divide it by, which the only thing I have is 240 volts. Divide that 240 volts into 72,000 VA, and you got 300 amps. Okay? And then when you come and look at this, the only thing that changed in this calculation is it's a 3-phase. So you'll notice in step 2, we got the formula there to sort of get you used to this. We're giving you 2 different options here to look at applying when you're doing this type of calculation. So the first one, we didn't have 3-phase. This one, in the exercise problem, we do have 3-phase. Okay?
Right.
Now, this one, I'm going to look at getting the kilovolt amp rating. Now, this is a little different because I'm trying, instead of coming back like I was the other, I'm trying to get to a rating. Okay? So in other words, I'm looking for the kilovolt amps where I have a 300 amp load supplied by a single phase 240 volt system with a 75% power factor. Well, the only thing you're going to do here is take everything, multiply it together just like you did, but the only thing you're going to do is divide it by 1,000, and that'll give you your KVA. I did exactly the same thing I did a while ago. The only difference here is I'm trying to get a KVA rating, and I divide it by 1,000. Okay?
Right.
Everything else was still multiplied together. All right? And then when you get over here, you got the exact same thing. The only difference is it's a 3-phase system. And if it's a 3-phase, you're going to have to put the 1.732 in there for the multiplication part, then divide it, or multiply all that together and then divide it by 1,000. Okay? And if anybody's getting confused on where to find the information, just look over here in the known values, and then you can work these problems and know where we're getting these different values from. All right? Now, looky here. Now I want to find the kilovolt amp rating. Okay? I got 300 amps load, 240 volt single phase. Just multiply everything together and divide it by what? 1,000. Yeah. Okay? What I'm trying to point out, I'm not changing anything here. It's just, what am I trying to find and how do I go about that calculation? But the main part I like to point out is you're still taking them loads, voltages, power factor, efficiency, and everything, and multiplying it all together. And you're either dividing into the watts or VA, or you're dividing 1,000 into it to find the load for kilowatts, amps, or whatever you're looking for.
Yeah, and one thing I want to bring up, James, and you kind of taught me this when we first started kind of going through this, about when we did the 100-foot rule, about the 1,000-foot multiplier. And I really enjoyed that. It taught me a lot because when we, just so everyone knows, when we first started talking about this, James had a thumb rule saying if you have to go over 100 foot, then you have to include voltage drop because when they first made the ampacity table, it's based on 1,000 foot.
It was, and it was burning conductors up. They realized they had a mistake. And actually, if you go back and look in the American Standards Handbook, and, we might do that after we get through all this, and I'll go through all of that again. But where we went in and we actually show where they would go in and they would say for like a number 14, once you got to like 65 foot or something, they wanted you to start looking at doing voltage drop. But the difference was when they put that in like that, that was for solid conductors. Now that you have the stranded, now it's just a rule of thumb. You want to start looking at that at 100 foot.
True.
Okay.
Yeah, I really like that, but that was just a little added extra thing where it comes to 1,000 multiplier.
And then when you get in, look in here, same calculation. Once again, we did the first one with single phase and the exercise. This is a exercise problem, and we're telling you it's 3-phase, so you need to take it at 1.732. So one of the things that we've tried to do through our publications, if you'll notice, we're showing you and highlighting in the middle there the formula you want to use for this calculation. Okay? Sure. So we're trying to help you out every way we can so you know what you're looking for and how to get that information. Now, this one is a little bit different because what I'm going to do is find what is my horsepower rating. Well, the same thing applies. You take the 460 volt, the 3-phase, you take the power factor at 90%, and you take the efficiency of the motor, which is 85%, and then you take, what is it pulling? It's pulling 48.98 amps, okay? Now, what you're going to do is you're going to take all of that, multiply it, and then since we're trying to get the horsepower, what is 1 watt good for? 746, so you're not dividing by 1,000, you're doing it by a watt. So you're going to take that 746, divide it into it, and it's going to tell you it pulls 41, or you have to have a horsepower rating of 41.7 horsepower.
Okay.
And this is a rule of thumb, the way that when the guys were out in the field a long time ago, they used to do this all the time. And anybody that listened to the podcast, we might get him to do it again. Dad did on the motors, and he was going in talking about the rule of thumb, how they would go in size the horsepower rating, and then he would look at doing the overcurrent protection device. He would tell you a rule of thumb, you take it at 300%, 200%. He went through all of that and showed you and it was based on the frame type of the motor is the reason they did it that way. So
tempo.
All right, and then when you
Juan, we'll check it out. We'll see. We always
love a guest. I just go in there and slap him, tell him to come in here and get to work.
There you go. I like it.
Say, oh man, you got work to do.
Yeah.
Now,
all right.
Same calculation here. All I'm doing is finding the value for the horsepower, and the only difference here is it's a single phase where the other was a 3-phase, and I had to take it at 1.732. So what we're doing, we're going back and forth in different ones because we want you to be able to see there's different ways to calculate this. Okay?
Right.
Now, let's say you looked at this and it didn't have a power factor. The only thing is, it'd still be the same calculation. You just leave off the power factor. You still divide it by 746 per watt, don't you? Okay? Now, that takes care of your AC/DC formulas. And that's about as easy as I can explain it, is just remember everything is taken, multiplied together, and depending on what you're doing, if say like you're finding the kilovolt amps, then you divide by 1,000, okay?
Right.
But if my kilovolt amps and everything's known, then I'm going to divide by the voltage and everything and get the kVA and take it at 1,000 and divide into it, okay?
Nice.
So it just sort of depends the calculation you're doing, and I think everybody understands that pretty well now.
Yeah, and that's awesome. Like, I like that little illustration you have there. That's pretty cool.
Well,
I've never seen that before.
We have this comes out of the design book, and it's also in the Journeyman, it's also in the Masters, and it's also in the generator transform motor compressor. And the reason it's in there is because a lot of times when you're doing these different things, you got to know Ohm's law, pi formulas, and all of that are where they're combined. Okay. And when I was going through school, this was taught to me. Basically, if you take your finger, put it over E, which is the voltage, then you multiply what the amperage and resistance is. If I put my finger over R, then you divide the amperage into the voltage. If I put my finger over the I divide the resistance into the voltage. That is basic calculations for Ohm's law. And then we'll get into pi formulas here in just a little bit. Okay?
Yeah, and it's basically like it's almost kind of like a triangle. So if there's anything that is unknown, then you have those two knowns that you could use to find the unknown.
Sure.
I like that.
It's very simple once you understand the concepts. And then I'm going to show you something when we get over and you've got the power combined with everything. So we're going to look at something a little different, and we're actually going to have a wheel for the power, for the voltage, for the amperage and resistance. And each one of those will have 3 different calculations for it. And we'll take a look at that.
Okay.
Now, it says, what is the load in a circuit where a current amperage of 4 amps and a resistance ohms of 30 ohms? Now, like I said, you just put your finger over the E, and what do you get? You get I time R, and you take the 4 amps times 30 ohms. That's going to give you 120 volts. It's pretty simple. Okay? And you're going to notice we're going to use a lot of the same values as y'all go through this. And then when you get over here, you got the exact same thing. Now, you'll notice we took right in there and we put the little wheel there, and you'll see we got it in green for finding the voltage, and then everything else is left and white to try to make it as simple as possible. Then we give you a basic circuit there showing you what the amperage and resistance is, and then you're going to multiply those together to determine your voltage. Now, when I get over here and I'm looking at finding the amperage, I put my finger over that I, and that means the resistance is divided into what? The voltage. I got 120 volts, and I got 30 ohms. I'll take 30 ohms divided into 120 volts, and that's going to give me 4 amps. Pretty simple, okay? And if you look, while ago we had 4 amps and 30 ohms, okay? So I'm keeping the same thing here. Now, when you get to this one here, you're going to have exactly the same values that were in that other illustration. And you'll notice once again, we got the current in green, and then you'll see the voltage is above the resistance in the wheel. So you're going to divide the resistance into the voltage to determine what the amperage rating is. Then when I go to the resistance, I got 120 volts again. I got 4 amps of current. So I take the 4 amps divided into the 120 volts, and it gives you what? 30 ohms. Okay? So
and I like this how people can go back and you could see like on the right hand side how there's all these little boxes that you can fill out, and you could actually do these calculations just so everyone knows that you can actually, do these calculations and prove that James is not gonna win the Willie Quiz tonight. Oh,
you never know.
Yeah.
I got 1 or 3 last week. Those were all guesses. They'll probably be all guesses this week.
Well, no, I try to make it a lot easier this week because I know that you're a good guesser. So,
all right, and then this one, same thing. You'll notice we got the wheel R, so you got the voltage above the current. So the current's divided into the voltage and determine what your ohm rating is. Now you're going to notice. And this is what's great the way we did this, because you can go back to the illustrations, or you can go back to the example problems we did and see the exact same values were used, and we still got the exact same values that we started with. Okay?
Right.
So that's why we did it this way. So, I've seen a lot of publications, they do all different types, values and stuff. We tried to keep all of ours the same. So when you go back and look, you can go, yeah, I get it. You know.
Looks like Juan has something to tell you. He normally lets the guys he mentors single phase, straightforward, 3-phase, requires a square root of 3, which is
1.7. Some put 1.73, some put 1.732.
Yeah.
We do 1.732.
Oh, David remembers the first day of his apprenticeship. The instructor told us that we were going to learn about ear.
That's what we are going to do, and we'll, after we get through all of this, and I'm going to do the voltage drop calculations, and I'm going to show it where you have a single phase, and I'm going to do one for branch circuit feeder. Then we're going to do a 3-phase and add the 0.866 on there. Okay.
Nice. Sweet.
Now this is pi formulas. Look, it's the exact same concept. Okay. If you're looking for the power and you put your finger over P, I time E. Okay. If I put my finger on I, E is divided into the power. If I put it over E, I is divided into P. Okay. Yeah. So these are pi formulas. Now let's look, we're going to keep it the same. You got 240 volts and you got an amperage of 40 amps. Okay. Tells me there, put my finger at P at E time I, so 240 volts times 40 amps gives me 9,600 watts. Pretty simple. Okay. Yeah. Same thing here. You'll see we got the power. There's my wheel there, I time E. We even highlight in the formula requirements there what the formula is, and you're just going to multiply them together to determine what the watts is. Okay. Now, I'm going to look for the amperage here. So I got 9,600 watts and 240 volts. P is over E, so that means I'm going to divide the volts into the wattage. So I've got 9,600 watts, which I just calculated, divide it by 240 volts, and it gives me 40 amps. So just like I did, the 40 amps times 240 volts gave me 9,600 watts. Okay? And then if you look here, we're going to use the same values again. There's your I. P over E, divide the E into the P, and that is going to give you, once you know the values, it's going to tell you what your amp rating is. Okay? Now I'm going to find the voltage. Put my hand over P, or my hand over E, and I'm going to divide the amperage into the wattage. So I got 9,600 watts, I got 40 amps, divide that into it, and guess what I get? 240 volts. Now, it didn't matter if I was doing Ohm's law or I'm doing pi formulas here. One is E-I-R, the other is P-I-E. Depending on which one, you just take your thumb. This is how you go about looking at performing this calculation. And then once again, here's my wheel. P is over I, so I'm going to divide the current into the power. Once I know those values, I'll make that calculation, and that'll tell you what the voltage is. Now, up to this point, I don't think anybody should have any problems under this. This is the basics, okay, of learning how to apply this. Now, what's going to happen here is where I'm going to get into the wheel of everything, and I'm going to show you some different things here that we'll look at. All right. Now, the first thing it's going to ask me here is I'm going to find what the wattage is. I've got 240 volts times 30 amps. We've already done this calculation. It's just like pi. P times I, or E times I, is going to equal 240 volts times 30 amps. They're across from each other. That's going to give you 7,200 watts. We've already done a calculation similar to that. Now, when you get over here and you're looking at the power here, depending on which one you have here, this is what I tell people to remember when I'm looking at power. If you come in and you're looking at applying, say you've got your amperage and resistance, or you have your voltage and resistance. The resistance, when I'm looking at power, is going to be single by itself, but everything else, the amperage and the voltage, you're going to square. Okay? Right. So now if I have the voltage I'm squaring, I'm going to divide it. But if I have the amperage, I'm going to multiply it. Okay.
Right.
And the way I like to look at this, and remember it in this form, this is the way I always think about it on the power, is I go back to the main wheels. So if I look at E time R, E is above R, isn't it?
Yeah.
So naturally it makes sense. I'll square it, but I have to divide into it. I and R are opposite of each other. So they're going to be what? Multiplied. Does that make sense?
Okay.
Okay. Every time I look at calculations, and basic calculations, it doesn't deal with code, I'm always looking at a way, how will somebody understand this to where it's easy to understand? And this is one of the main things I look at here is, when do I multiply? When do I divide? Well, and I'm looking at power. That's what I'm thinking. That's something I'd put in my mind a long time ago, is E's above R. So therefore I'm going to square that. And if I have the amperage, I got to square it, but I'm going to multiply it because they're across from each other. Okay.
True.
So those are things to think about.
And the other thing to think about is they do put the wrong answers on the test. So what I like to do is I like to do reverse, where I like to go take the answers and plug the answers into the formula, and then see if they make sense for the question.
Right.
But they do put the wrong answers on the test, so you guys got to watch out for that.
Sure do. Now, you're going to find the watch. You got the voltage and resistance. Now, I said E was above R, so I'm going to divide. Now, I couldn't do it in this program here. It wouldn't allow me to put the two superscripted, so I had to just put E2. But you would square here the 240 volts. The 240 volt square is going to give you 57,600 volts, and then I'm going to divide the 8 ohms of resistance in it, and that's going to give me 7,200 watts. Okay. Now, watch this. Here I'm coming in. I'm looking at the same thing. I've got my voltage here, 120 volts. You're going to square that, and then you're going to divide the 186 ohms into that squaring of what your voltage is. And then that'll tell you what your watts are. Okay. Now, here's one where I know the amperage and the resistance are across from each other. So I got 30 amps. I'm going to square that. 30 times 30 is going to give me 900 amps. I'm going to multiply it by 8 ohms. And looky there, what did I get? 7,200 watts, like I did before.
True.
Okay. So you're seeing I'm still getting the exact same thing. As I go through all this, you're going to see these wattage values, amperage, resistance, voltage, everything's going to be the same. And you're going to see how all this works.
Oh, nice. David has a clock at work that has that same wheel that you have on that. That's awesome, David.
David, I do too.
Well, and David has a good point too, that it's possible wrong answers. You just have to know what the right answer is. So.
Sure. And
that's a good observation, David.
It is true. And, like I tell people, if you'll just start with the basics here and understand how to apply the calculations, you're not going to have as much problem. And I promise you, when I get in and I start doing all the more complex calculations, you're going to see where I'll take some of this stuff we're learning right now and put it in there, and you're going to see it's not that hard. Matter of fact,
True.
When I first started with this, the first thing when I went to work with Dad, he said, I want you to edit. We had a book back then that covered every calculation in the code. I mean, we did x-ray machines, everything. I mean, we got into doing fire pumps and doing all the different things that were required there. We even have the calculation showing you the voltage drop for the fire pump, which is different than a normal voltage drop. And as I was going through it all, I started learning a lot of different little things. And one of the things we'll get to when we get there is I'll have some rule of thumbs I'm going to give everybody to go by. And you're going to see as we go through those rule of thumbs, if you remember this, it's going to make it easier for you during the test. But that's how
I remember it. I remember it.
I know you do.
it made my test way easy. Like anything that was electrical theory, I smashed it.
Sure.
You know.
And, it's just from doing it over and over and over, I learned all this stuff. And it was just because Dad made me learn it. And once I got that part down, then the next thing he told me to do was learn grounding. And we may do a whole grounding series, and then I may get into doing lightning protection for buildings and structures with NFPA 780. And I know everybody would love that, because that's something you really got to know what the hell you're talking about when you get into that stuff. But
100%.
This one here, same calculation. You had I and R opposite of each other, so you're going to multiply that. The only difference is you had to square the amperage. Okay. Now, as I look at doing the amperage here, and let me go back one here so you'll see the wheel. Here's my amperage right here on the bottom left-hand side of the wheel, and you're going to see everything looks exactly the same here. Okay, if you look, P is over E. Is that correct? So P is divided into E. E is over R, so R is divided into E. The only thing that happens different here is P is over R, but they're going to take and have you do the whole thing and then square it up at that point. That's the only difference in finding the amperage, but everything is still the same. Okay, and we're sticking with the exact concept that I've been talking about. Okay.
Right. Okay.
I suppose. Oh, yeah, that's true.
Wow.
Mm-hmm.
Yeah.
He's right.
Good comment, David.
And those are things that, and David's older like me, and David and I come through in the trade, and I'm sure David went through the same thing when we first started. The first thing they taught us were these basic calculations here. They said, if you don't know this, you can't do the rest of it. And then when we got into doing all of this, and they would tell us about 3-phase and single phase, doing all this stuff. And then they got into voltage drop, and I never forgot 0.866 just because of the 3-phase for the voltage drop. And then after that, then they started teaching us the layout of the code, and then we were off from that point on. So now this is the amperage, and you got the voltage and resistance. It's the same calculation we did at the first. The resistance is going to be divided in the voltage. So 240 volts divided by 8 ohms gives you what? 30 amps. Okay, we've already done this calculation, but the main thing I want to point out, we're still using the same values, aren't we? Same thing.
Yeah.
Hadn't changed anything. Here's the thing. We're pointing there to E divides by R. E is above R. And when you know how to use your Ohm's law and pi formulas, once you know that, then you know how you're going to apply this stuff here. Okay?
Right.
Now, as I go the next one, I'm looking at the amperage again. Here's 7,200 watts, and you got 240 volts. The P is above the E. So 7,200 watts divided by 240 volts gives me what? 30 amps. Okay? And when you get over here, you'll see we got the exact same formula here. P divided by E on the wheel. Once you do that, that'll give you what your amperage is. So anybody working these problems can go back and check this next week.
True.
Now, got one more amperage here. 7,200 watts, and I got 8 ohms. Now, the only thing you're going to do here, you're still going to divide the 8 ohms into 7,200 watts. The only difference is here, you're going to take and you're going to square root it. So I'll square root the 900 amps, which if I took the 30 amps and squared rooted 30 amps a while ago, what was it? 900 amps. It's going to tell you I equals 30 amps. I should have moved that I down one. When you're working late, I'll tell you. So just remember.
Dude, I'm telling you, like you really nailed it tonight, sir. I mean, you've done a good job. This is really good. Like everyone's been giving me compliments.
Oh,
how
really?
much they like it.
Well, thank you. I appreciate that. I actually, all these illustrations and everything we're showing you and all that, we've put a lot of time and effort into this stuff. And I think when people see the new illustrations that are going to be, and I'll say this will be used in our online training. Now, when we have the online training read, the only difference between seeing it here and the online where those blanks are, you can go up and click those blanks and fill in the values and work the problem. And then I've got in an accordion file underneath that gives you the answers. Now, and one other thing I do is if I have NEC sections and everything, over on the left-hand side of the illustration, there will be standards to review, and I'll have them in order by the steps that you would click to go and check to make sure you're doing it correctly. Oh, thank you, David. I really appreciate that, brother. Now, I'm going to look at the voltage here. So I got 30 amps and I've got 8 ohms. Well, just like the basic Ohm's law formula, I's across from R, so I'm going to multiply it. So we'll take 30 amps times 8 ohms. That's going to give me 240 volts. Pretty simple to follow, easy to do. Okay. Same thing here. You'll see we're doing the voltage at the top left-hand side. It's in green. And I times R, there's your formula. Even in the formula requirements, we have it highlighted. And then just multiply that together, and that's going to give you your voltage. Now, the next one I'm going to look at, I know the power. It's 7,200 watts. We know the amperage was 30 amps. So P is over I. So I'll take the 7,200 watts, divide it by 30 amps, and that's going to give me 240 volts. Okay? Nice. Now, as you can see, have I changed any values yet? Not one value's changed, and I'm still getting the same answers that I started with. Now, the other thing that's going to be a little different here is this one out here, and you'll have to remember this for the voltage, is they're going to take, and it's not going to be divided here. You're going to multiply on the voltage, okay? The amperage you divide by, but since we're doing the voltage, you want to multiply here, okay? And then you're going to square root it. So you're going to take the power and resistance in this next one, multiply it, and then square root it. But if I was doing it on the amperage, you divide by it because you're going down to a lower value. If you know the voltage has to go, it'll be a higher value. That's why it's multiplied. That's the way to remember it. Okay?
Yeah.
So when I look at this, I've got 7,200 watts of power and 8 ohms. So I'll multiply that. That's going to give me 57,600. Then I'm going to square root it, and that's going to give me 240 volts. Okay? And then when you come over here and you look at the power wheel, once again, same thing I was talking about, P times R, multiply it, square root it, and that'll give you your voltage. So anybody working these problems, you can see we're going to stay. And the great thing is going to be about this, when y'all start doing this in the illustration, you're going to see the same values all the way across. They're just going to be different than what I did in the example problems.
Thanks.
Now, here's where I get into the resistance. Now, basic Ohm's law, I get into this. I actually meant to put a divide sign there on the top one. That should be E divided by I. I did it in step 2. I was working late. So 240 volts is above the amperage, so I'll divide 30 amps into 240 volts, and that's going to give me 8 ohms of resistance. Okay? And then you come over here and you look at this, you'll see I'm going to do that calculation. I divided into E. Once you know those values, fill in the blanks, and that's going to give you your own value. Now, one of the things that you're going to see here is where you come in and you've got the voltage here, okay? The voltage, if you got the voltage and the power, you're going to square the voltage and divide by the power. If I have amperage here, I'm going to square root the amperage and divide it into the power, okay? So when you look at this one, you've got 240 volts and you got 7,200 watts. We're going to take the 240 volts, square, it's going to give me 57,600 volts, divide it by the 7,200 watts, and that's going to give you 8 ohms of resistance, okay? And then you look right here, take the That's interesting. I've got the wrong illustration there. Let's see. Oh, I've got them backwards. Sorry about that. That's my bad.
Yeah.
I put them in the wrong spot. So this in here, I'm actually showing it where the amperage, I got them backwards. This was real late at night. Anybody saw my post? I posted like at 3:15 in the morning for the High Voltage Live podcast. That's how late I was up last night getting all this together. But
no, we appreciate it. Like I say, if anybody has any issues, then you can consult the James Stallcup editing team.
It was me. I can tell you who did it. I'll go back and fix that for next week. I'll put that in the right spot. So here you've got E squared divided by power. Okay, so that takes care of it. Once you know what that is, do those values, square up the voltage, divide by power, and then that's going to give you what the ohms is. And then the last one that we have here is looking at doing where you know the power, the wattage is 7,200, and you have a current of 30 amps. I'm going to square the amperage, which is going to be 900 amps, divide that into the 7,200 watts, and that's going to give you 8 ohms. And there's your formula right there for finding the resistance. And other than that, that pretty much tonight is where I'm going to finish up.
All right, so what I need to do, I think I need to make the Willie Quiz to where you can fill in the blank. So when you get them wrong, and I'm just like, wrong. Filled in the blank wrong. But no, we really appreciate like everyone joining all our groups and everything, and following the podcast, everything. It's like been a lot of fun for me and James. And like I say, I've been brainwashing James for about maybe like 2 years now to try to follow me and like get to like I've been warping his brain to like say all my stuff is right and all his stuff is, like whatever it is. But but the whole thing is like it's really awesome. James is a really cool guy, and we've had a lot of fun. We like to joke around and just have fun doing these. Like I say, I got a lot of tour reviews, got a lot of different stuff. James is probably one of the best educators I've ever seen out there as far as just being down to earth and just, bringing you the code the way it's written. And, everyone says we teach our opinion, but, I mean, we're just teaching our opinion of what we see the code saying. So, I mean, if you guys have some other way that the code says something different, then, maybe we'll, figure it out. But, I think it's going to be interesting, 2026. We have a lot of public inputs out there.
It is. It's going to be interesting. I'm waiting to see on a couple of things. We'll see what happens.
We're not out there to, like, bash anybody. We're just out there to get clarification in the language. So I think it's going to be interesting because, like, either way, the way mine are voted on or whatever, it's going to be interesting because we're going to be like, is this an outlet? Is this not an outlet? Like I think it's funny when they say, oh, that's a hardwired or corded plug connected. It's like, okay, well, you have GFCI protection twice in the code. Like, why would you do that?
No.
You know what I mean? There's no reason to. So it's going to be interesting, but let's, I guess, go to the tool.
All right.
Time for tool review of the week. Sponsored by Electrician's Only Tool Review and Nipex Tradesman.
Alright, so it looks like we are coming into a Milwaukee week, and this is a really cool tool that I came across. One of my buddies was telling me about it. This is like a portable power generator, and It's really sweet because I guess what you do is you charge up these batteries, and then you can take it and you can power up like your on-demand different devices that's shown on the right. So you could go watch the game out on the job site, power up different stuff. When it said like 3,800 watts peak, like that's a lot. I mean, you could do a lot of stuff with that. But the thing is, like, this is almost kind of like it's weird because when I saw it originally, it says generator, but it doesn't really generate anything. It's like an inverter,
Yeah.
So it basically just provides you power. You don't even have to, like it's just kind of a cool little thing that I saw. I was like, wow, I was like, this is really cool, Like they're starting to do this stuff where this is basically what I call UPS, So this is like a battery powered backup system where you could use it for like your office and just have it charged up, and then if you lose power, then you still have portable power. And, I mean, you could run like some pretty big tools off 3,600 peak watts. I mean, that's a pretty big inrush. It shows a whole list of things that you could run on it, but I really like this. A new tool from Milwaukee. I really like it. Like I say, if I was gonna buy a Milwaukee right now, this is the one I'd go buy. So.
I think that's pretty cool because you don't got all that noise and everything, and that's actually pretty cool. I actually like it. I had to go get me one of those. I didn't know they had those.
Yeah, well, it's time to try to get you on the first question
of the new year.
First question of the new year.
The critical branch of the hospital essential electrical power. I bring those on. I think they made some changes because they made some changes in 51731, but I think this is in 51734, if I'm not mistaken. I don't remember the exact subsection, but if I remember right on this, I'm sort of, golly, it's been a long time since, but I think it's both. I think it's C. It's both of them, isn't it?
Well, we are going to have to give you a correct answer for the first time in 2024. So C is correct. It is both one.
We just need to stick with code questions because I do good on those.
Yeah, well, I'm wishing you luck on the Willie Quiz. I mean, dude, the thing is, I really made this one easy, dude. You're a good guesser. So that's how you go 3 for 3 because you're good at guessing. And so then what I do, I think about your guesses, and then I go in, I formulate them off your guesses. And I'm like, all right. I was like, cool. This is going to be a really easy quiz tonight.
All right, let's cue that. Let's see what the hell you got going on tonight.
You are now entering the zone of the Willie Quiz. Enter at your own risk.
All right. Thanks for everyone joining tonight. Willie Quiz. Feel free to post your answers in the chat and try to beat James tonight. He's only been defeated several times.
One time.
All right. At least 2. At least Daniel's got you 2 times. But all right. So in 2017, only 1 out of 70 cars sold were electric. Today, 1 in every blank are electric vehicles. Is it A, 1 in 10, B, 1 in 20, C, 1 in 14, D, 1 in 7, or E, 1 in 35? Good luck, everyone. All right, James. So I know that you always do. Oh, here comes Daniel J out of the blue. Oh, dude, Daniel J is hungry tonight. He is going 1 in 10. Oh, Daniel. So.
He just been waiting, hadn't he?
if anyone missed out, James actually made a podcast about how Daniel J already has all the answers and. He was hating on him, but awesome answer, Daniel. You're not going to influence James's answer. Dude, James usually copies Daniel, just so everyone knows. James usually copies Daniel, but... Alright, so... Daniel has a good answer right out of the gate. That's pretty good.
You know how I feel about electric cars. I don't think there's that many or so as many people think.
Okay.
And I do know, and we are talking about cars here. We're not talking about the bikes and all of that. So I think it's the lowest number you can go. I'm gonna go with D. I think it's probably 10, but I'm going with the lowest number because I just don't think there's that many worldwide out of the cars sold.
That's actually opposite. So you're saying
1 out of every 7.
So you're saying 1 out of every 7 electric vehicles. So you're basically saying opposite. So you're saying in 2017, only 1 out of 70 cars sold were electric. Now today, every blank, so basically, like Daniel's saying, 1 out of every 10 are electric. So if you're saying 7, that's way low. You're basically saying almost every car sold is electric. So if you wanted to go the other way, you would say 1 out of 35. If you're trying to have the reasoning, I'm fine with.
I'll
if
stick
you want
with
to say,
D since I already said it. I already called it, so I'll stick with it.
All right.
I missed it, but that's okay.
All right. So James is, I guess. Sorry, Daniel. Sorry that he didn't copy your answer this week, but James got it right this week. Oh man, I don't know how you got that one right, but your whole logic was 100% wrong. But all right,
I already caught it. I read the question wrong.
Yeah, so it's all right. I tried to talk you out of it, but it's all good. You got James nails it. Answer D for question number 1.
I'm going to consider it wasn't really the right answer. I've already given it because I read the question wrong.
Yeah. Everyone knows, all my apprentices know I'm always rolling 7, so I'm going to always put a question in there. It's going to be a 7.
I actually know this one.
All right.
You finally gave me one, I know. Stop damn.
All right. So, blank country leads the way in proportion of new electric vehicle registrations. Is it A, United Kingdom? Is it B, Sweden? Is it C, Norway? Is it D, China? Or is it E, the USA? Good luck, everyone. All right, so Daniel J comes out the gate right away, going with a C. Awesome. Daniel comes. I don't know. There's been an increase, a lot of increase over in China, and the USA has really had a lot of increases. So sounds like James is gonna just directly copy Daniel tonight.
I am. I already had it. I'm going Norway. I remember this one, and China is number 2, if I'm not mistaken.
Well, there might be some changes in 2023. So, I mean, this is not something I'm really going to like to do, but I have to give you both the correct answers. C is correct. It is Norway is correct.
Was China
I was thinking
number 2?
Yeah.
Yeah.
I was going to try to get you on that one, but, oh, man, you got me.
I didn't know that one. I was right when that was I got one. I finally don't have to guess.
All right. So this one's really easy. You guys should get this one off the top of your head. So the first ever electric car was built in blank in the UK. A, 1901. B, 1898. C, 1929. D, 1884. Or E, 1890. Good luck, everyone.
Well,
all right, so this is a chance.
It's D or
this
E.
is a chance for Daniel to actually beat you, because what we have set up is the tie. If the guest ties, then they win.
Let me go first, so it won't say I'm copying.
All right.
I think I'll go with D. It's D or E. I'll go with D. I know it was early.
All right, so Daniel has the chance to win with an E answer. If Daniel ties James, then he will win tonight. And the answer is D, 1884. Oh, man. Oh, James somehow just swipes it away from Daniel. Daniel, really good answer. I was actually putting that in there to try to fool James, but oh man, really good contest tonight. Daniel, you could tell that James, he's trying to Google really hard to try to figure out how to beat you, brother. So we're gonna I'm gonna have to send you the message. I'm gonna have to send you the answers before, so that James can make a podcast about how you know all the answers and you don't know how, and then when you tie, then we might have to have a bonus round. We might have to get a bonus round set up for people that tie.
Sometimes I go 3 for 3, 1 for 3, 0 for 3, 2 for 3. I honestly, I do not know the answers. I guess that all of them, unless I just know it. And I just guessed at the last one, and the first one I misread it, but the second one I actually didn't know.
It's all good. Yeah, he's going for the lowest. I should have had one even lower. Now I know. I'll be all right, he just goes for the low one. I'll be 1, 2, 7, or 29.
Well, you notice I picked the 2 lowest ones. I was I know it was in 1800s, and I was I think it had to be one of the 2 lowest, because I remember reading about that a long time ago.
Yeah.
And I knew it was 1800s. I just didn't know the right date.
All right. Well, thanks for jumping in, Daniel. It's good that James is his guessing is on par, because he's dude, Daniel just come out dude, Daniel's gonna try to defend himself from your podcast that you made about him being a Daniel's like a hack. He's like Daniel's just latching on to me. Daniel's riding my coattails and just like trying to steal all my answers and try to beat James and stuff, but it's all good.
That's fun.
Yeah. All right, let's do Wall of Shame.
All right.
Shame. 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 Shame.
All right. I can't remember who we stole this from, but it was a guy doing a service call. Oh, okay. There you go. You got it in there. Yeah. Thanks, David, for... we stole this from the Wall of Shame, and this is the official disconnect outlet. So we always said that it couldn't be an outlet and a disconnect. Yes, it can. All you have to do is just pop that cord out the wall, and then there's your disconnect outlet. So it is classified as a disconnect, and it is an outlet too. So I said it didn't exist. We were saying it couldn't exist. It exists.
That's funny.
It's a disconnect outlet. I knew you'd like that one.
I tell you, some of the things we get on this show just crack me up. Like, God dang, there's people actually out there doing that crap. God dang.
Yeah, I have one of those in my house. I don't even know what it goes to. I think it was like something they like did, like when they were like building a house or something, and. When I saw it, I was like, okay. I was like, just plug that in if I need something to work, maybe.
State of the art, baby.
Yeah. The good old disconnect outlets. But, dude, it's really awesome that you're putting together these, Journeyman exam preps. I really appreciate it. The whole reason I made the NEC Code page is because I really enjoyed the Journeyman exam questions. I try to post them every Sunday. And if you guys have any problems with the questions, you don't like it, then just hit me up, and I'll try to make them better, edit them, make them make a little more sense, whatever. But a lot of these, I'm not doing all of the questions myself. I do some of them on my own, like if I run across them out in the field. Daniel knows firsthand that I get a little passionate when I run across things. I'm like, oh, dude, I'm doing code question on that one, Like, because I see it, and especially with this whole bundling thing that we ran across, I run across so many myths. Like, I already have like 3-4 myths already down the line, just because all these people are like, oh, do this one. Oh, yeah, we hear this one all the time. Inspector failed me on this, And I'm like, really? I was like, Inspector failed you on that. I was like, what code reference did he give you? Oh, no, he didn't give me a reference. He just said 90.4. I was like, okay, that's actually illegal. They can't do that, Yeah. So it's really fun. It's really fun to do these podcasts. I really appreciate everyone joining every week. Means a lot. And just letting you know, James, the Avs are playing your Stars right now, brother. So
they are?
Yeah, so... Yeah, and guess who's number one? The Avs, baby. Number one in the Central.
Are they winning?
I don't know what the score is currently, but I don't have
they're
the
losing
game.
at the end of the second, 3-2.
Well, that's not losing. That's just like barely, not even, like McKinnon will come back on that one, That's not even nothing. But anyway, I'm saying we're number one in the Central.
Well, that's because you played 2 more games in Dallas.
No, we have 2 less games played.
You played 38. We played 36.
Oh, okay. On the games played.
We're 3 points behind you.
Yeah.
After tonight, we'll be 1.
We'll see. You could come back. I'll give you that. You could come back, but we'll take it at least into overtime. Get that 1 point, But
I don't even know hardly anything about hockey.
Yeah.
I just learned recently what the hell offsides was. I mean,
Dude,
like soccer in a way.
I will be honest. I really do love the Dallas Stars goal song because it was made by Diamond Darrell from Dimebag Darrell from Pantera. So their goal song is Pantera song. So I do like that, and I do listen to it every now and then. But right when Dallas goes to score the goal, I just shut off the the goal part of it, and I just listen to the Pantera part of it. I don't listen to Dallas scoring a goal part.
That's funny.
But like before the horn sounds, I mute it, and then I just listen to the Pantera part,
Nothing wrong with that.
So yeah. No, it's all good. I really appreciate everyone joining us every week. It's always a lot of fun. I have just such a good time doing this. James has such a good time doing it. I think we had a really good content. Just make sure to subscribe. We'll just keep bringing it every week. And the more people we get to subscribe, like the better it gets every week. So that's just going to be the awesome part. I think James is on board with that. So Daniel, make sure your grandma subscribes, your aunt, your uncle, your cousin, like everyone, all Daniel's friends. And then what's gonna happen is James gonna make a podcast about how all Daniel's relatives love his content, and he needs to start donating to
Yeah, anybody watching, tell other people, electrical or engineer and whatever, tell them come over and subscribe. We got this next year, there's going to be a lot of stuff updated, going to be added to it. And by the time end of the year gets here, I plan on having over 500 videos at a minimum on there that cover different subjects and stuff. And by the next year, it'll be over probably getting close to 1,000 on there. So, we're just going to keep adding to it. And then if you want to study it online, you can go online and do it. If you want to buy a publication, we got that. There's just a whole lot of stuff going on this next year. It's going to be a hell of a year coming up.
So Daniel knows firsthand what I do on some of my stuff. Like, we had these pre-manufactured buildings come in for gas and oil. And I was like, watch, I'm going to take a picture of this pipework. I'm going to say my apprentice bent this today, And it was weird. I don't even know why they even did it like they did. It 90'd up and 90'd over, then came down, then went through an LB. They're expecting some shelf to be there or something weird. I don't even know why they did it. But I was just like, yeah, look, I'm teaching my apprentice how to bend pipe. And oh man, Daniel was like, dude, he's like, you think they're gonna really freak out on that? I was like, oh yeah, dude, anything with pipe bended, oh man, they're gonna freak out. And he was just blown away. He's like, whoa, dude. He goes, you got 400 comments on that. It was so funny. And it was all pre-manufactured, so it was all bent at the factory. So the whole entire places. So I started just taking pictures of all these different places. And I'm like, yeah, my apprentice is doing really good bending pipe now, and everyone's like, oh, you need to teach him how to not do 90s and just run straight, you know what I mean, or whatever. And it was so funny because you could take a picture of a straight piece of pipe and just say, this is the most beautiful piece of conduit I've ever installed, and everyone will be like, oh, no, you need to take the sticker off, or oh, you need to do this, or, whatever. It's just so funny the amount of comments you get, so I really appreciate everyone out there that, follows Nat King Code, joins up with the Stallcup Electrical Education channel. It means a lot, Daniel is one of my students, and and he's right, man. They nitpick everything, Daniel, and Daniel's like, hey, how many people do you trigger this week? I'm just like, not telling you, bro. Not telling you. It's confidential. Yeah. Many. But really appreciate everyone joining. We'll probably go ahead and just sign this off. Thanks, James, for all the great content you bring every week. And, I'm glad that you got lucky with my easiest quiz ever this year. And so, you're just going to be going down the whole
Start
rest
the
of
new
the year.
off right, baby.
Yeah, you're just gonna be going down the hole next year. So, the rest of 2024. So, thanks everyone for joining. Really appreciate it. Thanks for following Nat King Code, and remember, make every day an easy day.
We'll see everybody next week. Have a good weekend.